Alrighty, there was a problem in the, I'm looking at the wrong folder. Interest calculator homework, alrighty. Edit folder. If we look at the assignment, I tried to simplify it for you, and I failed. How did I fail? Okay, now I'm not seeing N. Did I upload a corrected version of it, but not upload a correct PDF?
You replace N with 12. So it's in there. In class you said to the power of N times T, but there you have 12 times T.
Right. Okay. So, the correct format of the formula, if you wanted to make it an absolutely perfect compound interest calculator, you would replace all the instances of 12 in my formula with N. And you would have to ask them how many times, per year is it calculated. But compounding monthly is a very common thing, so I just hard-coded 12 as N.
And is that comma stand for to the power of?
This is how you raise to the power of the POW function. We haven't talked about that, but I gave it to you so that you could do the problem. Very, very good question there. Let me pop open a new notes. We have our normal operators, like x is equal to 3 plus 2. Y is equal to x times 4, right? Z is equal to y minus 100. And A is equal to Z divided by 2, right? We have all those. There's another one called modulus. So plus, minus, multiply, divide. Forgive my grade school fondness for calling them plus and minus rather than add and subtract, and times and div. Hey. This is modulus. It means remainder. And if you've taken a CIT1173 course, you know what modulus means. We'll hit it later. Unfortunately, there's something missing. There's no exponent. In Python, you could use star star to indicate exponent. Maybe y'all are used to typing 3 to the power of 6 like that, or whatever, 3 to the power of 5. You can't do that either. Instead, you have to use a POW function. So there is no exponent function, exponent operator. An operator is a symbol that does math. So you have to use the POW function. So 2 to the power of 3. If you wanted to do this, x is equal to 2 to the power of 3, you would have to write it like this. X is equal to POW 2 to the 3. If you want to do y is equal to 10 to the power of 20, you would have to do y is equal to POW 10 to the power of 20. So in that formula that I gave you, need to close some things down, excuse me. That's what that means. It means take this value and then raise it to that value. Okay. All right, surely we went past chapter 1. Maybe not. Yeah, we did. Okay. So why isn't chapter 2 saved? I know we started it. I guess we never started chapter 2.
That's chapter 2.5.
Well, I see a chapter 2 here, but that's for the C# users. So, whenever you're looking in D2L and you click on a PowerPoint, don't use their little preview here. Instead, download it. The word preview is great, But you know, you might have a 100-page PowerPoint document. The little preview window is really lousy, so just download it and open the PowerPoint that way. So the parts of a C++ program. Haven't we done this? Isn't this looking familiar? Alrighty. Where did we stop? So you can use ENDL. They call it the manipulator. Yeah. So if you send ENDL to an output stream, like cout, it causes it to go to the next line. But there's another way to do that as well. You can use \n. Like this. Programming is \n fun. When do I use one and when do I use the other? If I'm already in a string, if I already have a quote open, it's faster just to type \n, end quote, rather than type end quote, arrow, arrow, ENDL, n, you know. So that's my rule of thumb, is if I can just tack on /n at the end of a line and have it magically work, that's great. Otherwise, I go ahead and do it like that. You know, when would that be? Like if I just printed out a number, like that. I wouldn't want to do \n like that after I already had x, after the quote was already closed. It doesn't really matter though.
For the /n?
Yes, /n has to be in quotes. And that's an L, not a 1. So the include directive. It's known as a preprocessor directive, meaning that preprocessing happens before the compilation happens. When we hit the compile button, what it does is it goes and it grabs the file specified and it inserts it into the source code. Behind the scenes, we never see that happen. So anything that's in that header file is now part of our own C++ file. And that's not part of the C++ language itself, it's part of the tools that help build programs. So it's known as a preprocessor directive, and there are several others, but the one we're going to see most often is #include. And all preprocessor directives start with a hashtag. There are other ones such as #if if something is defined. There's all sorts of them, but #includes the important one at this point. Don't put a semicolon at the end of it because it's not a C statement. Variables and literals. Did we talk about naming conventions? What are valid names and what are invalid names? Does that sound like a yes or a no in this class? I'm going to look at you, Olivia. Have we talked about those? No? Okay. So a variable is a named location in memory. There are valid names for them and then there are invalid names. Valid names for variables are letters, like the word apples. That's a good identifier name. That's a good variable name. And you can mix numbers in. Apples 2017, whatever. But it has to start with a letter, not with a number. You can't make it 2017 apples. So it needs to be all letters or numbers, and there's a couple of symbols you can get away with using. Underscores work and $signs work. I think $signs work. I always get confused because one of the slides says that it doesn't work, and then I test it and it does. Let me prove that to myself. All right, so for example, I have these variables here. What is your age and what is your height? Could I have declared a variable with a $sign in it, like payroll? Yeah, you really can, even though the textbook says that you can't. But do people put $signs in their variable names? No, it just looks really weird. So let's write some rules for variables. #include is a preprocessor directive. It includes the contents of a header file into your C++ program. That's about enough of that. All preprocessor commands start with a hash. Variables are named places in memory that have a type and hold a value. int x is equal to 3. The name is x. The type is int. And the value is 3. Variable names. They should be meaningful. If you just say x is equal to, long calculation, that's not very useful. But if you can put, current temperature, that's a bit long, but is equal to long calculation, whatever, that means a lot more. We were looking at the PDF of the homework assignment. All these single letter variable names are pretty tacky. Let's rewrite them with better variable names. Final is okay, but how come we didn't call that deposit? How come we didn't call this rate? N may actually be a perfectly valid term for that. And then T was the number of years. Why didn't we call that years? Now that makes a lot more sense. Right? We can actually read that. You could if it wasn't chopped off the board. There we go. So using good variable names helps. If it looked like this, double F is equal to D, or P for principal, times power, whatever, that's technically correct, but it's much better to use whole words. On the other hand, am I going to use whole words every time I'm up here typing? Probably not, because if I can just use a single letter and y'all understand what it means for the time that we type it, then you're not going to make typos, right? If I used current temperature as my variable name and I used it a whole bunch and you had to type in current temperature, it'd take us half an hour longer to get through it. So I might just call it temp, T-E-M-P. Single letter variable names should be avoided for anything except for counters and loops. We don't even really know what a loop is yet, unless you've taken an earlier class, but just kind of remember that. Avoid single letter names for anything except loops, even if you see me use them up here in code samples. So variable names should be meaningful, can be letters, alphabet letters, digits, and underscores or dollar signs. Book says no to dollar signs. Underscores are very common. Patient age is equal to 30. That's fine. That's a perfectly good one. You can also do what's known as Camelcase. Patient age is equal to 30. Camelcase because it's lowercase until you hit a hump. Then, uppercase, like a camel. It's got humps. Didn't make it up. This is the more common style nowadays that a lot of people follow. I learned programming using underscores, so I like the way they look. You can use whichever one you want. So, tax 1978 is a good variable name. I forgot the other rule. Can be letters, digits, and/or in those symbols, but cannot start with a number. Cannot start with a digit. Tax 1978, is that a good variable name? Is not a good variable name because it's got a space in it. Variable names have to be one word, no spaces. $1978 tax. No, not good. Can't start with a number. Tax underscore 1978 is good. Tax star 1978. Would that be a good variable name? No, because the star means something else completely, right? It means multiply. So really the only symbols you can get away with are underscore and dollar sign. Can't use exclamation marks or minus symbols or whatever. A literal is a number, is a value that's typed directly into the code rather than something that's read from a file or you let the user type in. There are some literals in this program here. Apples equals 20. That's a literal. It's literally typed into it. It's an integer. It doesn't have any decimal points. These are also literals. These are strings that are embedded in the code. If you wanted it to say something other than bushels, like you wanted to say barrels, you would actually have to edit the file and then recompile it and redistribute it before the end user saw the word barrels rather than bushes. So to some extent you want to avoid hard coding values if you can. For example, if you were going to write a program that had a tax rate in it, you'd want to make the user able to change the tax rate without having to actually edit the source code. You'd want to be able to make a configuration file or something that specified the tax rate, or have some way, other than just so-called hard coding a literal value in it. Am I going to use the word literal or not? A lot? Not really. Identifiers. Identifiers are variable names, but they also represent functions, classes, things like that. Our main method in our code, right there, that's also an identifier. Follows the same rules. I could put numbers in it if I wanted to. Well, I couldn't because then main wouldn't work. But if I wanted to write another function, void my new function, like that, and put some, I could give it a wacky name with lots of underscores, and maybe some dollar signs and some numbers, whatever. That's a valid because it doesn't start with a number and it doesn't have any illegal characters in it. Names are case sensitive. Where I have a double age is equal to 0, if I then turn around and do if age equals height, do something, that's not going to work. It doesn't know what age, all caps, is. It doesn't know what height, all caps, is. They have to match exactly. And a lot of people, when they're typing, will make a very simple mistake. They're used to having a capitalized word, so they'll do if age equals 32. Do something. Looks good, but then you have to go and look, oh, it was supposed to be a lowercase letter. Yes, Olivia?
What's the difference between two equal signs and one?
Very, very good question. What's the difference between two equal signs and one? One does a copy. One equal sign means copy that value into that variable. Two equal signs does a comparison. Is age equal to 32? If you try to do this, that doesn't make any sense because you're essentially asking height is compared to 0. Well, you can't really do that unless it's inside of an if statement. So whenever you write an if or a while statement, you're going to use two equals. Pretty much every other time you're going to use one. Does that make sense?
Yeah, thanks.
There are technical terms for those things. Let's go ahead and do them. Write them down. We had our operators, being our math operators. But then we have equal, which is known as the assignment operator, because it assigns a value. It copies. And compare equal is the equality operator. It checks to see if two things are the same. So you do x is equal to 3, and then you do if x is equal to 3. So this assigns a value, copies a value, and this compares the value. Some languages won't even let you compile if you mix it up, if you write this, if x equals 3. The reason they don't let you do that is because what would happen? You're hitting this if statement. What's it doing? Well, it's not going to compare x to 3. That's 2 equals. So it just goes ahead and erases whatever was in x and writes a 3 into it. Did you mean to erase it? And 99.99999% of the time you didn't. If you type that into this editor, it'll probably give you a warning. Maybe not. See, it's valid code in C++. It's okay to copy 32 into age in the middle of an if statement, but would you want to? Would you want to erase the value of the age? No, you don't. So, if statements need two equal signs. So a variable name, one of the rules is that it cannot be a keyword. The keywords are the words that define the language. Words like int, and void. We haven't really seen very many keywords. As you see here, there's a whole bunch of them. Are we going to learn all of these? No, we're not. We're going to learn a fair subsection of these. So the keywords define the language.
Are all those are all of those included in the rudimentary, or are some of those like modules? Like,
Well,
are there more that you can get from modules?
some of them represent more complicated programming concepts than we will hit. Things like do and else and not and enum and new and long and short. Yeah, we're going to use all that stuff. But then there are some things like bit and bit or and ASM and decal type and stuff like that. You wouldn't use those at all because they're just concepts that we're not going to hit in this book, if that makes sense. You could. All of that's perfectly legal stuff. You don't even need to import a new library and to use them because these are keywords. They're built into the language. But, it's just like English. English has, like 10,000 commonly used words, and then there's, another 10,000 that are less often used, and then there's another 10,000, that are very rare or whatever. They're common words that you're going to use, and we will learn, a subset of those. So variable names should represent the purpose of the variable. Items ordered, that's a good variable name. It's in Camelcase because it's got a capital letter in the middle of it. It has to be an alphabet or an underscore or a dollar sign. After the first character, you can use any alphabet characters you want, and numbers and underscores. Uppers and lower cases are distinct. So, can't use a dot in the middle of a variable name. Sometimes you'll see a dot in our code, but it's not really part of a variable name. So that as a variable name would be illegal. Total.sales, that's wrong. Fourth quarter sales, no, that's wrong because you can't start with a digit. Total sale dollar sign, is that legal? Book is wrong. Yes. Maybe they're trying to train people not to use it. Integer data types. We have all sorts of different data types in this language as opposed to Java, which just has far fewer. And the reason for that is when C was invented, memory was incredibly expensive, and like a megabyte was an unheard amount of memory. That's 1 million bytes in your computer. And if you think back to the computers that people bought in the early 80s, like the Apple II and the Commodore 64, those things didn't have megabytes of RAM. They had 64K, that's 1,000 bytes rather than 1 million. So they had data types that would represent small numbers. And then as time has gone by, people keep adding new data types. Well, I wanted big numbers. I didn't want a number that was just between negative and positive 32,000. Okay, so I'm not, that's a short int. That's that size. A normal int is that size. Why can it hold more? Because of the size of it. We talked about bits, didn't we? The more bits you have in a data type, the larger the value it can contain. An int in this version of C is 4 bytes wide, which is 4 times 8, because there's 8 bits in a byte, is 32 bits. It can hold a much larger number, up to 4 billion. If something is unsigned, it can hold a larger value, a larger positive value, but no negative value. I think I talked about that. If I didn't, just trust that if you make something unsigned, you can hold values that are twice as large, but you don't get any negative values. So a short int can go up to 32,000 and up from minus 32,000. If you make it unsigned, it assumes it's always positive. There's no way to have a negative one. Then you have still the same range of numbers, 65,000 different numbers, but it starts at 0 and it goes up to 65. Do you need to use unsigned? Most of the time you don't. Most of the time, you don't care. You like negative numbers, right? We like numbers to be negative. So we're probably not going to use unsigned, ever. Do you want to use short ints? Not really. Why do you want to limit yourself to numbers with a maximum of 32,000? Yeah, you could. You could say, okay, a person's age should never be above, 100 or so. So why do I need, to be able to go up to 4 billion? Just use int all the time, unless you need a number larger than an int. If you need something that goes above 2 billion, then go to what's known as a long int. And you can leave the word int off. So you have ints and you have longs. I hate that name, long, I'm sorry. I feel silly saying it, but that's what we got to do in this language. Other languages just call it a long, the single word. So you have ints, which hold up to 2 billion, and then you have longs, which hold up to, 9 super centillion, quadrillion, whatever. Vastly larger numbers. Integer means that it's a whole number. It doesn't have a fractional part. There's no decimal point. If you try to store a fractional value in it, it'll round it down. So if you say int x equals 3.9, after that, x is just equal to 0. Excuse me, 3. Let's talk about that. Integer types are whole numbers. There are short int, which go up to about 32,000. There are ints, which go up to about 2 billion. And then there are longs, which go up huge. How about that? Whole values only, so floating point numbers get rounded down. If you say int x is equal to 3.5, when you're done with that, it's really only equal to 3. Yep, it still rounds down. It always rounds down. If you say int x is equal to 4. X equals 3, x equals 4. That actually has some important consequences. Because if you write something like this, yes?
Does it make it more lean if you use the short int? I mean, would there be a reason why you'd want to even use it?
If you're writing in an environment that is so starved of memory that you need to worry about each and every bit like that, then yeah, sure. But it's not going to make it run faster or anything like that. And the difference at most is going to be like, just a couple of bytes per variable. So you'll know if you're that desperate. Yeah. And that's a very good question, We grew up using computers that didn't have that much memory, and we don't want to be wasteful and stuff like that. But in general, you can get away with just using ints.
So it's not going to run it faster if you're
Right.
using a smaller.
Exactly. It's not going to run faster or slower if you use a smaller size. Okay. So if you do int x is equal to 5 divided by 2, you might think, does it equal 2.5? No, because it gets rounded down. So it's now equal to 2, right? 5 divided by 2 is 2.5, rounded down. That has serious consequences. The equation for the volume of a sphere is this. 4 over 3 times radius cubed. Now, there's all sorts of things wrong with this, right? This is the mathematical expression. It's not computer code. So let's say we take a stab at it. We say int area. Well, that's our first problem, is why would we use an integer to store, volume? Because it might not have an exact rounded off number. And certainly, and I forgot pi. Pi times radius to the power 3. That's the volume for the volume of a sphere. So int volume is equal to 4 divided by 3 times pi times POW radius comma 3. That kind of expresses it. But 4 divided by 3, if these are integers, rounds down. 4 divided by 3 is just 1. It's not 1.333 or whatever. So if you have to hard code an equation like that, it's best to go ahead and add decimal points like that. So it won't do that integer division and that round down. have another example in mind, but I'm not going to bother saying it. Why 4.0 and 3.0 to prevent integer division, which rounds down to the nearest whole number. I always hit that rather than that one because they're both red. Here we go. So you can define variables on separate lines or on the same line. And on some code example that I gave in one of my classes, I had this. I had x equals y equals z equals 0. And somebody said, what does that do? It sets all of them equal to 0. Is there any reason to do that? No, you don't have to. You could say x is equal to 0, y is equal to 0, and z is equal to 0. That's totally valid code. Both of them work. Both of them work just fine. But when you're declaring them, you have to give a type and then a name, like that. If you want to, you can define multiple variables of the same type on the same line. It's very common to do that. Int x is equal to 3, int y is equal to 4, int z is equal to 5. Now, would you keep redefining over and over and over? No, no, this is just like pretend each one of these is in its own module. So this can be rewritten as this, right? And this can be rewritten but not respelled as int x equals 3, y equals 4, z equals 5. That's kind of a personal style thing. I think there's an advantage to putting one on it per line. Why? Because you can document them more clearly. What if you did this? Int h, comma, w, comma, t, whatever. It's real hard to tell what those are, whereas if you did this, int h, height, int w, height in inches, weight in pounds, and then int t, temporary variable, whatever, or temperature, whatever, something like that, temperature in F. You can't give good comments if they're all stuck on one line, right? Instead, if you define them like this, you can put a comment defining what that variable does, saying what your variable does. Now, if you give good variable names, do you have to put a comment there? If you did this, height, inches, int weight, pounds, and you did int temperature F, do you need comments? Not really. But it's not a bad idea to document all of your non-trivial variables. If you're asking for somebody's height and weight, then when you define your variable, put a comment saying that it's a height, and then put a variable saying that it's a weight. So when we defined all of the variables for that interest program, int in number of months, or whatever, number of times per year, compound n times a year, and then int p, principal, whatever, It makes sense to do that. It's better to give yourself good variable names, but at the very least, whenever you create a variable, go ahead and put a comment. Am I going to remember to do that every time I'm up here typing? Probably not, but I'll try. But variables of different types must be in different definitions. So if I do float or double, a double is a double precision float. If I need to measure somebody's temperature down to the fractional point, I wouldn't use an int. So double temperature is equal to 98.6. I couldn't mix that in with a bunch of ints, right? I couldn't do int x, y, and then O in temperature and hope that it figures out that temperature is really supposed to be a double, a floating point, so that it could hold whole numbers. Fractional numbers. No, you have to define them separately. So ints go on one line, the doubles go on another, the strings go on another line. Listing each one on its own line is a nice way to do it. Since I usually have limited screen space up here, if I'm using single letter variable names and their purpose is really clear, like X, Y, and Z, you know, in a 3D space, I may do int X, comma, Y, comma, Z, just because that saves two spaces, you know, 2 lines of code, me having to scroll up and down. I haven't made y'all type anything yet. So an integer literal, there's that number again. If you hard code, if you type into your programming, if you type into your .c file a number and there's no decimal point, it's an integer literal. If you type in a number but it does have a decimal point, it's a floating point literal. Other textbooks call them unnamed constants. 15 doesn't have a name, but it does have a value. Just tossing it out there. Delete that. Here we go. This program has variables of several integer types. It's got something called int for checking. It's got an unsigned int for miles because your mileage would never go negative. And then it's got a long for days because we might need to take a journey that's going to be more than 2 billion days long. So here are our literals. Negative 20 is going to get assigned into checking for whatever purpose. 4,276 is going to get copied into miles, and then days is equal to 1,890. So we have made a journey of that many miles. Our checking account balance is, I'd rather that be our checking account balance rather than negative 20. And then about this many days ago, Columbus stood on this spot. Really? In Oklahoma? Cool. So numbers are stored in memory as integers by default. If you need to make a number bigger than 2 billion in your compiler, then stick L after it. Or it looks silly, but in my code, if I needed to make a really large number, like long int US debt, you know, is equal to whatever it is, 9 or 12 trillion or whatever. I'm exaggerating. But anyways, if you typed that into the code but didn't type in an L at the end of it, it would try to treat that as an integer, and since it's larger than 2 billion, it would give a syntax error. So if you need to type in a literal larger than 2 billion, then tack on LL at the end of it. Does that mean that when the user types a number in, they're going to have to be throwing L's in? No, no. This is talking about inside the code when you're putting your own numbers in like that. So, yes, sir.
The user puts in a number that's larger than 12 billion, will get a syntax error unless you...
If you store it in the appropriate data type, a long, it'll work fine. If you don't store it in an appropriate data type, it'll round it to a weird value. Let's actually do that one. We haven't typed in any code. Let's make a new file. File, new, project.
Let me also tack on to a question for that.
Yeah.
If you said if it's exceeding 2 billion, what if you were to like take like the square root of that number and it was less than 2 billion and you squared it by itself? Would you still have to do it by LL? So like, say for instance you had 4 billion and took the
Well,
square root of that and then squared it and made that.
Well, you would have to do 4 billion LL and then to the power of 0.5, which is square root it, and then you could store it in an int, right? Although since a square root is rarely going.
Root and then squared it and used that as your value. Would you still have to do LL?
Yeah, I would. I would. When you say have to, I don't know. We might be able to jigger it so that you don't. But generally, if a number is going to exceed at any point in the journey the maximum size for the data type, we need to define it that larger type. Okay, so I'm going to make an empty project. I'm going to call it September 5 because that's today. Go to source files, add, new item. our good old boilerplate. I'm not going to even say it aloud. Pound sign include IO stream. Pound sign include string using namespace std. Void main system parentheses pause. You Macs and Linux users won't add that. There we go. Okay, so let's ask them to type in a number, but we're going to make it an X. I mean an int, excuse me. So cout, type in a big number. And then let's read it in. CIN goes into X. Now let's just print it out. Cout, you entered, or X equals, arrow, arrow, ENDL. Nope, arrow, arrow, X, arrow, arrow, ENDL. All right, that's kind of a silly program, right? Type in a number and then print it out. But it will prove a point. Sorry, I hid all the code. I'm just going to test to see if it works first and then let you finish typing it. Type in a big number. Okay, 99 is a big number. X is equal to 99. Once you get that code, run it, type in something like 99, and then type in a huge number, like 999 trillion, you know. Figure out how many zeros you have to add. A trillion is a number followed by 9 billion. 9 billion will work. Billions are numbers followed by 9 zeros. Trillions have 12 zeros. Sorry, I spaced out of that. Type in 9 followed by 9 zeros, or 9 followed by 12 zeros, and see what it prints out. And it's not going to be 9 billion. It's not going to be 9 trillion. All right, the suspense is killing me. I'm going to do that. Type in a big number, 9 followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 billion. And it says you typed in, or X equals. Does that look like 9 billion to you? No, it doesn't. What happened is known as overflow. Overflow is when you exceed the value, the largest value that that data can be stored in, and it kind of wraps around to a negative version of the value. We could talk about the bits again and explain what overflow is doing. So at any point, if your data ever exceeded the size of the data type that it was expecting, you could get overflow. So that's why I'm saying that if you square rooted something and then squared it again, then it's likely to have suffered overflow, just meaning that it's no longer a valid value. One of the, did I show you all the Pac-Man illustration of the maximum Pac-Man level you can reach? Okay, this didn't show getting there, but after you play 255 levels of Pac-Man in the arcade, when it tries to load up level 256, that level is being held in a single byte value that's only 8 bits wide. The maximum value that an unsigned byte can hold is 255. So it adds 1 to it, but that's too large for a byte now. So the byte value is invalid. It wrapped all the way back around to 0. It tried to draw level 0. The computer has no idea what level 0 is in Pac-Man, and so you get a whole bunch of garbage. You cannot play past 255 levels of Pac-Man. That's the end. So, you know, people who are nuts about these kind of things try to play perfect games. The maximum number of points you can get all the way up through level 255. And then there's a maximum that you can hit, because once you get to this screen, you can't progress. So that's an example of of overflow causing a bug in a program. Now, is it really important for Pac-Man to end at a certain point? No, not really. It's probably actually not a bad thing at all. The guy's been sitting there playing for 18 hours. He probably needs to take a break. But would it be a bad idea for your Patriot missile to, suddenly crash because it's run more than 255 days in a row? That'd be a serious problem. You would not want to use a byte value, something that holds very small values, for, a value in...
So could you make a new Pac-Man and run it on a bigger memory?
You can edit the source code for Pac-Man. It's all just in machine code. People have taken the ROM chips from Pac-Man games and imported them into the PC so that you can play them in emulators. And if you go in and you hack a few different numbers, you can get it to work right. You can convince it that when it hits 0, it's actually level 1, and keep going. I had that on the screen. I didn't make sure that everybody saw this. This worked for everybody, right?
Yeah.
So let's make a new one. Let's make a long or a long int. You don't have to type in the word int. Long y. Same thing. Cout, give me a big number. Cin into y, and let's print out the value of y. Cout arrow y equals, end quote, arrow y arrow endl. And I should not have typed that below the pause. Make sure pause is the last thing in your code. Why? Because anything after that pause disappears as soon as you hit enter. You would never get to see it. Now you can type in a large piece of data. Type in a big number. Okay, I know that this isn't going to work for an int. Oh, neat. That botched completely. Delete what we just did. Delete those 4 lines, but change x from being an int to a long, like that. That's what our code should look like. Then run it and type in your 9 billion or your 9 trillion, and it will actually work. 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So a long can hold up to 9 trillion. It can hold numbers far larger than that. That also has real consequences if you're like doing multiplication and the multiplication can hit above 2 billion. So for example, I don't know what the square root of 2 billion is. Let me go find out what the square root of 3 billion is. 3000. 0.5. Okay. So 60,000 squared would be way more than 2 billion. So do this. Cout 60,000 600 squared is, end your quote, add a couple more arrows, and then type 60,000 times 60,000 arrow endl. And there we go. Here we see overflow happening again. 60,000 squared is not negative 6 billion. But what 60,000 squared is larger than 2 billion, so it could not fit into an int. So it wrapped it around. How would we fix that? We would want these to be treated as longs. If you go in and you add L's to them, in the Java programming language it's a single L. And then you ran it, it'll print out a better value. See? That's actually worked.
And Does it have to be caps lock house?
I don't know. It would look like ones though. See, that looks like ones. So even if it did work,
So would it be beneficial just to start using long as like a default process for everything?
you certainly could. On the other hand, how often are, it does kind of depend on data type. It's kind of like int is your default unless you need something larger. But you could use long as your default, but if you're talking about somebody's age, you're asking for their weight, you know, you're calculating the number of seconds in a day. Yeah, go for it, go for it. You can use long. I will not give you a reason against doing that.
One more question.
Yeah.
So the reason we have an issue with integers exceeding 2 billion, is that because of actually how many integers are in the number? Or like, say for instance, you had a float followed by 10 zeros, which were 10 zeros and then a
It's
1.
because an integer is a 32-bit data type. And the maximum value that 32 bits can hold, and I really don't think I've given this lecture. I think that I skipped it because I gave it to the Java students and I felt sorry for the Java students having to turn around and then sit through this. So we're going to talk about bits and how they represent numbers and a maximum value that can be held. But maybe we did do the short term, the short run of it. If you have bits are zeros and ones, if you have 8 bits, the maximum number it could hold is 255. If you have 16 bits, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15. You know what? I'm not going to type all those zeros. But the maximum value that 16 bits could hold would be 65535. In this language, that's known as a short int. 32 bits can hold up to about 4 billion. That's unsigned. So if you make it signed, you can go from negative 2 billion to positive 2 billion. That's an int. And then 64 bits is huge. How can you calculate these values yourself? You take 2 to the power of 16. 2 to the power of 8 is equal to 256. So I should have said 256 different values. 2 to the power of 16, 65536. Why am I having to go up from 65535 to 65536 when I write these? Because this is how many different values you can hold, but if you count at 0, you can only go up to one less than that. So like if you have 10 different digits in your counting system, what's the highest digit you can have? 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So anyways, and then 2 to the power of 32, whatever that is, it's pretty large. It's easy to find out. Let's just go into Google. 2 to the power of 32. It's 4 billion. And then 2 to the power of 64 is absolutely huge. 18 followed by 18 zeros. So that the time when you will encounter this recently in your real life or your computer life is that recently, and by recent I mean within the last decade, Windows made a jump from 32-bit Windows to 64-bit Windows. 32-bit Windows, the largest amount of RAM that you could address, memory in your computer, was 4 gigabytes of RAM. You could not install and access more than 4 gigabytes of RAM in your 32-bit Windows. 64-bit Windows, you could install vastly larger amounts of RAM. I'm not saying that you could install that many bytes of RAM in your computer. It is limited by, you know, they do set, you know, upper limits, but you can see that it's certainly much larger than 4 billion. All right, almost belaboring that too much, but I don't mind because you were asking questions about it, which I love. The character data type. The character data type is a single byte. meaning it can only hold very small numbers between 0 and 255. That just happens to be enough to hold letters. You know, we don't have more than 255 different letters in the English language. We have capital A through capital Z, lowercase a through lowercase z. We have all the numbers. We have all the symbols that you find on the typewriter. All of that comfortably fits into a single byte. So the char data type will hold small values or characters. It's a single byte of memory. And when we talk about what ASCII is and stuff like that, I did not do a lecture on ASCII, right? All right, then we'll see why they say that a C is equal to a 67, and an A is equal to a 65, and a B is equal to a 68, or whatever. It's just a small data type. So strings, words, names, when you type in Jeff, it's actually just a series of numbers that are stored in your computer. Character literals. If you want to refer to a character, which is a single letter, you put single quotes around it. If you want to use a string, you put double quotes around it. So if I was going to define some data types, you know, or I could do string name is equal to Bob, I could put double quotes around it. But character C is equal to whatever, you know, Y. Something like that, you have to put single quotes around it. Does this mess up if you try to use single quotes here and here? Indeed it does. In Python you could do that, in this language you can't, in most languages you can't. Would it mess up if we tried to use double quotes here? And again the answer is yes, that would fail. A lot of programming languages, including this one, are very specific that a character has to be one and only one character, one and only one thing between a pair of single quotes. Whereas a string can be a whole bunch of things. It can either be no things at all, in which case it's called an empty string. It looks like this. String empty is equal to that. That's an empty string because there's nothing between the double quotes. Or it could be 10,000 characters long. You know, string, the Declaration of Independence. I don't know what it is. Now is the time for all good, you know, whatever, you know, here, I'm failing my civics test because I don't know what the Declaration of Independence is. But whatever, you know, it's a long document, whatever. So that's a string. It's a whole bunch of characters. If you pulled out each individual character, you could do that. You could store each individual character of that string in a different variable, char variable, if you wanted. Kind of coming up to the idea that we're not going to have a programming assignment today. So you could write something like this. Character letter. Letter is equal to single quote A, and then if you print it out, it's going to print an A. Cool. Real useful. Letter is equal to B. See out letter like that. That can only contain one thing, though. One letter, one little single digit, one typewriter key press. So a character string is a series of characters. If you see hello here, what's going on is in the RAM of the computer, there's an H, or the number that represents an H, followed by an E in another byte, followed by an L, followed by an L, followed by an O, and then followed by a special character, the null character, the null terminator, because otherwise it wouldn't know when to end. So this is what the word hello looks like stored in your computer, except in real terms, each one of these is a different number. And in real terms, underneath that, each one is just a series of zeros and ones. But so that's what a string is. It's a sequence of characters. And it ends in a special character, null, which means 0. That's the end of the data. I'm getting tired of blathering. We're almost done with the class, though, aren't we? I think let's stop here and let's have a lecture that actually involves useful code that we type in and a homework assignment that we have based on that on Thursday. So usually we're going to do a half and half mix of code that we type in lecture, but this one wound up being lecture heavy.
Do you want us to turn in the...
Yeah, let's go ahead and upload that silly little program we wrote, though. So I'll make a Dropbox for it.